Welcome to this explainer. Okay, today we're taking on a really fun mission. We are going to completely transform what a lot of people remember as a dry, maybe even intimidating math concept into what it actually is, a totally practical, real-world superpower. We're unlocking the hidden geometry of our world by demystifying trigonometry. Let's get into it.
Just think about this for a second to really set the stage here. How exactly do engineers accurately measure the distance across some massive, treacherous canyon without actually crossing it? Or think about video games. How do developers plot out these entire sprawling 3D worlds right out of thin air? Well, they aren't just guessing. They're using this incredibly elegant mathematical tool that was invented purely to solve these exact kinds of impossible, real-world problems.
So, let's dive right in. The secret is literally right there in the name. Trigonometry comes directly from the Greek words trigonon, which means triangle, and metron, which means measure. And really, that's the whole game right there. It is all about mastering triangles to find unknown distances and angles. It's essentially the ultimate measuring tape for the physical universe.
All right, let's get grounded. To measure the physical world, we first have to break down the ultimate shape, the right-angled triangle. It has three core components, and they're all based around our target angle, which we usually call theta. First up, there's the hypotenuse, which is always the longest side, guaranteed. Then we have the opposite side, which sits directly across from our target angle, and finally, the adjacent side, which runs right next to that angle. Once you know these three players, you basically hold the keys to the kingdom.
Now, I know that looking at a scientific calculator can cause a little bit of math anxiety for some of us. Sine, cosine, tangent, usually abbreviated as sin, cos, and tan, they sound incredibly complicated, but they are simply ratios. That's it. They're literally just the length of one side of our triangle divided by another. Sine, for example, is just the length of the opposite side divided by the hypotenuse. Nothing more to it.
So, what does this actually look like in practice? Let's say you type the sine of 35 degrees into your calculator. It's going to spit out roughly 0.57. But what does that number actually tell us about the real world? Well, it means that for absolutely any right-angled triangle with a 35-degree angle, the opposite side will always be 57% as long as the hypotenuse. It literally does not matter if the triangle is the size of a tiny piece of paper or the size of an entire city block. That ratio is a universal constant.
Okay, let's put this superpower to work. Picture this. You're standing in a park, looking up at this towering tree. You obviously can't reach the top to drop a measuring tape down. But let's say you have a laser measure, and you know you are standing exactly 20 meters away from the top of the tree, and you're looking up at a 45-degree angle. Watch how effortlessly this comes together. Step 1, we set up our ratio. We want the height of the tree, which is our opposite side, and we know our laser distance is the hypotenuse. So we use sine. Sine of 45 degrees equals opposite over hypotenuse. Step 2, we just plug in what we know. The sine of 45 degrees is about 0.7071, and our hypotenuse is 20 meters. Step 3, we just multiply both sides by 20 to isolate that missing opposite side.
And boom! There's our triumphant result, 14.14 meters. We never climbed the tree, we never even left the ground. We just used a simple, elegant ratio to measure the unreachable. I mean, that is the literal magic of trigonometry, solving a real-world problem.
All right, here's the plot twist. Just when you think you've got this neatly boxed into the triangle category, the whole story shifts. It turns out trigonometry isn't just about triangles, it is actually the fundamental mathematical language of circles too.
Enter the unit circle. Think of a simple circle sitting perfectly on a graph, its center right at 0, with a clean radius of exactly 1. Because the radius is 1, as a point moves around the edge of this circle, tracing through those positive and negative coordinates, it constantly forms new right triangles with the axis. That radius of 1, that's our hypotenuse. This elegant little shape lets us directly measure sine, cosine, and tangent as points flow in this endless, circular wave.
Since we're spinning around a circle now, we have to talk about rotation. And we measure this rotation using two different languages. You're definitely familiar with degrees, where a full rotation is 360 degrees. But in advanced math, they use a standard language called radians, which is entirely based on pi. So a full rotation is 2 pi radians. A straight line is just pi. It's the exact same rotation, we're just using a different vocabulary.
Now, a circle is an infinite loop, right? You can literally just keep spinning around it forever. Because of this, trigonometric functions just repeat their values continuously, over and over again. And this gives us a brilliant rule for calculating things. If you ever have a monstrously large angle, you just subtract full rotations, subtract 360 degrees until you're back down to a normal number. And if you have a negative angle, you guessed it, just add full rotations.
So here's how we tame those infinite loops in reality. If someone throws a curveball and asks you for the cosine of 370 degrees, don't panic. That is literally just 10 degrees past a full circle. Subtract 360 and you're left with the cosine of 10 degrees, which is a nice, neat 0.985. What about a negative radian, like the sine of -3? Just add one full circle, which is 2 pi, or about 6.283. You get the sine of 3.283, giving us -0.141. It makes calculating these crazy angles absolutely painless.
Okay, let's step out of the infinite loop and bring it all back to where we started. Remember how we said right-angled triangles were the core? Well, it turns out trigonometry is a master key. These tools work for general, ordinary shapes too, not just ones with a perfect 90-degree corner. We call this solving triangles, which is just a fancy way of saying we're finding any missing side or angle in literally any triangle you might encounter.
The logic here is incredibly satisfying. Take a look at this setup for finding a missing angle C. We know a universal rule. The inside angles of any triangle will always add up to exactly 180 degrees. Always. So if you know two of the angles, let's say 76 degrees and 34 degrees, you just subtract them from 180. Boom! Angle C is 70 degrees. This leads us to the ultimate rule. If you know any three pieces of data about a triangle, sides or angles, you can almost always calculate the missing three pieces.
Now, for those of you wanting to level up to true expert status, I should probably mention there are 3 more functions hiding just beneath the surface: cosecant, secant, and cotangent. But honestly, don't let the new names scare you. They are literally just our original 3 core ratios, sine, cosine, and tangent, flipped completely upside down. Hypotenuse over opposite, for example. It's the exact same basic ingredients, just a reverse recipe.
As you keep leveling up and playing around with these concepts, you're going to start running into what mathematicians call identities. Think of these as unbreakable universal laws, or like cheat codes for math. Trigonometric identities map out rules that are always true for right-angled triangles, while triangle identities give you the advanced blueprints to manipulate and map literally any triangle in existence.
So we started today with what seemed like a dry high school math term, and we've ended up with this profound toolkit. We've seen how simple ratios unlock the heights of trees, how circles create these infinite mathematical waves, and how just 3 little pieces of data can map completely unknown geometry. So my final question for you is this: armed with this incredible capability to define the unreachable, what missing pieces of the world will you measure next? Thanks so much for joining me on this explainer, and keep looking for that hidden geometry all around you.